This is a table from another textbook. Breaks down the groups. They do say act strongly, moderate, weakly. Activating, a little bit different from my group. I hand wrote in what my group is, group 1. Both of these are group 2. I'm sorry, that 1 is group 2. Group 3, group 4. Basically, it's just a table slightly different than my groups, okay? One thing I want to point out here is that the amino group is a strongly activating group. Yeah, group 1. Okay? Different forms of amine, primary, secondary, tertiary, OH. But under acidic conditions, that is, if the reaction has acidic conditions or maybe a Lewis acid, okay, the amino is converted into a strongly deactivating group. Why is that? The amine becomes protonated, and now the nitrogen takes on a positive charge. And if the nitrogen is protonated, it no longer has a lone pair, and now since it has a positive charge, it's electron poor. So now that sounds like group 4. So under strongly acidic conditions, amines are actually metadirectors, or I should say at this point, deactivators. So the reaction conditions can change your activating, deactivating effect. Okay, Roman numeral 2. Let's look at directing effects. If you take anisole and nitrate it, standard conditions, nitric acid, sulfuric acid, you get this outcome here, distribution. 45% is orthonitro, 55% is paranitro, and less than 1% is metanitro. So you get 2 predominant products here. You get ortho and para as predominant products. Thus we call the methoxy group a ortho-para director. What groups will be ortho-para directors? Any atom that can donate somehow will be an ortho-para director. That is, it will promote the formation of ortho and para products. Any atom that can donate, anyhow, somehow, either by resonance or induction. So which groups can donate? Yes, those can. Yes, those can. Which groups in my groups 1 through 4 can donate? Well, if you can read, it's 1 through 3. Okay, 1 through 3 can donate. Group 4 cannot. Groups 1 through 3 are thus ortho-para directors. Now, is group 3 a net donator? No. No, it's not a net donator. It's actually a net deactivator, withdrawer. But can group 3 donate somehow? Yes. Yeah, it can donate by resonance. That's just not its main effect. Groups 1 through 3 are ortho-para directors. Boom, done. Group 4, which can only withdraw, is a metadirector. To illustrate that, look if we nitrate nitrobenzene and try to put another nitro group on. Standard conditions, 90% will be meta-nitrobenzene or meta-dinitrobenzene. The next nitro will go meta compared to the first one. You do get a small amount of ortho, but it's not significant compared to this. This is basically a meta outcome. Meta is your predominant product. Thus, the nitro is called a meta-director. Okay? Well, nitro is group 4. All group 4 groups are meta-directors. For example, if you take this compound here, we don't have a common name for this. It's the methyl ester of benzoic acid. But if you brominate it with bromine and like iron catalyst, or pre-catalyst, standard bromination conditions, so you're going to brominate this, where's it going to go? It's going to go meta. That's going to be your major product because this is a group 4 meta-director. We'll explain why on the next pages. Another example. You take bromobenzene. You try to iodinate it. Standard conditions, iodine and an oxidant. Cupric chloride. Where's the iodine going to go? What type of group is bromine in terms of director? Ortho-para director. You're going to get some ortho and some ortho, some para as your main products. Ortho-para directors typically get 2 products. It is a mixture. You would have to purify these and separate them. There's occasionally some reasons why para may be favored. Why may para be favored sometimes? Or what's an argument for why para might be favored? Sterics. Because this carbon is blocked. Okay? It's like, here we go, I got a big bromine here and you're trying to attack here. Okay? Sorry, no, attack here. You can't, I'm in the way. If I turn around, you can attack, or we can bond. But there's no blockage here. So you might say it's more favored to go para, yeah? Ah, but hold on. You got twice the chance of going ortho because there's 2 ortho carbons.
Sure.
So because there's twice the chance, you may get more ortho. That's why way back up here, actually para was highly favored because, I mean, there's 2 orthos. You can say like, the ortho you get like about 22%. 22% here, 22% there. Adds up to 45%, same product. Where in this position was only 1, you got, okay? So a lot of times para is favored, but still there's going to be significant ortho in it when you have an ortho-para director. Why are certain groups ortho-para directors, meta-directors, etc.? Well, it all has to do with, well, what's the rate determining step in an EAS? Formation of the sigma complex, which is carbocation. Putting your new group on different positions gives different intermediates. Let's see if we can explain that here with a methyl group, which is what type of director? It's group 2, so it's ortho-para director, yes. Okay, let's do 3 different attacks. Ortho, meta, and para. Some type of electrophile. Sometimes arrows aren't really shown that precisely. This looks like the electrons are sort of doing this. They're hinging up, leaving the bottom as a plus. Okay? You can always draw resonance structures of the sigma complex carbocation. Always. Electrons over gives this, electrons down gives that. Carbocation here. And then from there, you can remove an H and you can get final product. For example, you can take that H, move electrons in. It's the same, it's just the resonance structure of if the double bond was there. But right here, we've seen this before. Right here, we see the effect of the methyl. How's it stabilizing that cation? Inductive donation seen in that resonance structure right there. Okay, do para attack. Electrons sort of hinge this way, leaving plus here. resonance, resonance. But right here, what do we have? Induction of the methyl. What if you do meta attack? This is sort of hinging, we're going to hinge down, making bond to E, leaving top plus. And we can do resonance. Plus here, resonance plus there. Note, if we attack meta, we never get a resonance structure with a plus on that carbon where the methyl can donate and stabilize it like a tertiary cation. The plus never falls there. So we can't do like that and like that. So the methyl is not having as great of an effect. So ortho and para have more stable carbocation intermediates due to that right there. Meta you don't have there. So the meta intermediate is going to be higher in energy and thus less likely to form. Let's look at another example about the amino group. Question?
Is the para more stable because it only... Never mind, that's my question.
Go ahead and ask it so we can hear what you were thinking about.
Because the resonance, I mean, you only have to go one resonance structure, and then you're out to stabilize with the methyl. And the other one, you've got to like swing around to 3, but that's not... These aren't real, these are things down.
No, the resonance is there. Resonance is all over the place. We just did it step by step the board. What you're really going to do is draw the hybrid. The hybrid is there, the methyl is donating. Let's look at an amino group. Basically, all we've done here is replace the methyl with an amino. So I'm not going to repeat any of the introduction to this. Now here, if we have a methyl here, we would say inductive donation. But instead, how does an amino group going to stabilize? It'll stabilize by resonance. Inductively, nitrogen actually withdraws compared to carbon. But it donates by resonance. If we donate by resonance, we actually get another resonance structure, and it's going to look like this, with a positive charge on the nitrogen. But that's okay because it still has an octet. And we now have 4 resonance structures. Which one is the most favorable? The one in the box. Why? Well, charge on the nitrogen is actually the bad thing about it. More bonds, all atoms have an octet. Okay? This resonance structure is the one that really illustrates the effect of the amine. If we go para, you also get here, donate by resonance gives that again, and this really illustrates why it stabilizes this intermediate. But if you go meta attack, the plus never falls on the carbon where the amine is. And so you can never draw that resonance structure. So this intermediate is not as stabilized as the ortho and para intermediates. So it's not going to be as likely to form. So these are going to be your favorite pathways because stabilization of the intermediate, in this case by resonance. This all comes down to really stabilizing carbocation intermediates and being able to draw resonance. Now let's look down below. The NO2 group, which is what type of director? Meta director. That implies that the intermediate that comes from meta attack is more stable. Isn't that what that implies? Yes. Let's see why it's more stable. If we do ortho, we get the same thing. The only difference between the other two is now this, instead of a methyl or an amine, it's now a nitro. Plus falls right here. Does the nitro stabilize the plus? In this case, it does not. I mean, that's a dipole. There's no way to draw resonance there to that carbocation. The nitrogen is an electron-poor atom. It's actually bad to have a positive nitrogen next to a positive carbon. So the one in the box here is actually bad. Destabilizes. Ortho attack gives a destabilized intermediate. You also get that by para attack. Destabilized intermediate. What about meta attack? Do you get that? No, the plus never falls where the group is, and thus you do not get, there's no stabilization here. What there's not is destabilization like ortho and para. So meta is your preferred intermediate, and that's why nitro gives meta product as the predominant outcome. Now in the example we had like 7 or 9% of the ortho product, or whatever it was. Okay? So it did this sum, but that could be depending on how you do it. It's like water running downhill. I mean, if you got a lot of water running downhill and it can go like this, you say, hey, the water's going to go here, right? But if it's coming real fast, a little bit might go this way too, because it's coming too fast. Right? You ever see like a ton of water running downhill? Some might go an odd way because there's just so much energy. Depends on how that reaction was run. Nitro is a meta director. Any questions about these resonance structures or why certain groups? Of course, you're going to have to look at this stuff. Hopefully, you've already been doing it. Let's look at additive effects. We did that with activation, deactivation. Now let's look at it with directing effects. What if you have multiple groups? So, what if you take, what do you want to call this? Like maybe paramethyl benzoic acid? Okay. What if we try to chlorinate it with chlorine, aluminum trichloride, Lewis acid? Where's the chlorine going to go? Well, what type of group is the methyl? Orthopara. What type of group is the benzoic acid? Meta. So actually they're both directing where? They're both directing here. That's meta to this group and it's ortho to this group. So this I call reinforced direction. They're both directing to the same place. Now, the para position, this is an ortho-para director, but the para position is already occupied. And typically you're not going to put another group there unless it's very unique. So does that make sense in terms of reinforced direction? Thank you, Warren. Hopefully that's pretty straightforward. Let's look at opposing direction. Para-ethyl anisole. Methoxy, orthopara director, yeah? About the ethyl group? Orthopara director. What if we try to sulfonate this? Where's it going to go? Ortho to the ethyl or ortho to the methoxy? Well, the answer's already there. How do you get the answer here?
More stable. Group 1.
The stronger electron donator directs. That should make sense. We're looking at stabilizing the carbocation intermediate. Which one's going to stabilize it better? The methoxy stabilizing by resonance or an ethyl stabilizing by induction? The resonance from the methoxy is going to be a greater stabilization. It's going to be ortho to that, which is actually meta to the ethyl, even though that's an ortho-pair director. Cause, which one directs? The strongest donator directs. Group 1 is going to direct preferentially over group 2, etc. So there, this is a clear answer here. The methoxy will clearly direct, and this is going to be your predominant product. Larry?
In the sulfanilamide lab, we added the first halogen, and there was reinforced direction on the first halogen, but when we added the first halogen, then we had that third group that contend with, which I guess would be an opposing direction at that point.
You actually have two opposers to where you end up with, okay. Pretty much, it's very tough to beat a better director. Your group 1 is going to win out even if you have like 2 or 3 of the weaker directors.
Okay.
In general. For as much as we want to look at it. We'll see if we see some other examples. Okay, here we're going to, that was a clear winner up there. Here's not going to be so clear. What if we got, well, you could call this 4-methoxyphenol, hydroxyanisole. It's probably called phenol. It's probably called 4-methoxyphenol. But here we go. Both of them are ortho-pair directors. You try to sulfonate here, where's the sulfonic acid going to go? They're both group 1. Which one's going to win out? It's going to be a mixture of products. There's no clear winner here. They're both group 1. Probably not. It might be 49-51. What you're going to have is 2 predominant products. It's not going to be 95-5. Probably going to be 60-40, something predominant. And in terms of just predicting the product from a textbook manner, it's 2 major products are to be shown. Now there are some group 1s where you might say, hey, this one should be a stronger stabilizer than the other. But not there really. Look at another example. What is this? 3-chloro, was benzonitrile on the list too? No? No. I don't think it was. That's called benzonitrile. 3-chlorobenzonitrile. We brominate it. Where's it going to go? Type of director is the nitrile group, cyano group. Metal director, chlorine's orthopara, so where's it going to go? Let's circle the, first off, which one's going to direct? Stronger activator. Which one's a stronger activator? Chlorine. You gotta be careful, chlorine is not actually an activator. It's actually a net deactivator. But it's not as strong a deactivator as that, because that's group 4. So this is going to direct. So ortho-para means ortho-para. First off, how many possible isomers could you get from monobromination? 2. Why 2? 3. I mean, ortho, there's 2 ortho positions in para. Are these ortho positions the same? No. No. Now the cyano group is directing here. Of the 3 positions that the chlorine is directing, which one do you think is preferred? basically all of them. I think two of them. I think it's better to say this way. Which do you think is least preferred? That's probably least preferred, but because it's between the two existing groups, and so it's going to be harder for the electrophilic bromine to get there. What do I say here? I show all three products. Bromine in between. That's ortho to the chlorine. That's ortho to the chlorine, but the other position, that's pair to the chlorine. So I pretty much say all three are likely. That's probably least likely because of sterics, getting the group in between the two existing ones. This is vanillin. If you eat like vanilla wafers or something, you'll be eating vanillin. Basically, synthetic vanilla. What if we tried to brominate vanillin? Standard conditions, bromine and like FeBr3. There's one product that's going to be the major product. Can you show them one major product that's theoretically predicted? How does that look? Pretty good. How we do? So Ronnie?
Can there be more because both the alcohol group and the methoxy will be ortho-para and they're equally both group 1?
You said the phenol group and the what?
And the methoxy.
And the methoxy? Okay, this is ortho-para, so it's going to direct there, there. Okay. This is ortho-para, so it directs just there. What type of director is this? Meta, so where does it direct?
On the square.
You got two groups that are directing here. If that group wasn't there, it would be like opposing. But that group, which is it's really not a director, it's an avoider. Cation wants to avoid that. How does it avoid that?
Meta.
By going meta. Out of the night, yeah. So you really have two groups that are directing here, and only one that is directing over there. Does that make sense? These two sort of are equally strong, but that makes you go here. And indeed, if you brominate vanillin, you get that product right there. That's known as the major product. Does it make sense, Jordan?
Yeah, I just had a question. So if you had like two group 2s, could those overpower a group 1 or no? Their strength is like massively different.
That's what was asked for a little bit earlier. And typically, no. We haven't done that, have we? You're not thinking we did that here, did you?
No.
Yeah. Now, I could probably find you an example of like a group 1 and then maybe 3 group 2s. That's 4 existing groups, and then the 5th group, I went non-ortho-para to the group 1 group. Probably out there somewhere, but for us, we're going to say no. Got a group 1, it's going to always direct over a group 2, even if you have 2 group 2s.
Eventually, you run out of spaces in the benzene ring.
Right, and also you're going to, well, it has to go ortho-para maybe. Yeah, you only got 6 spaces on benzene ring. What about this down here? This is 2 rings. We nitrate it. Where's the nitro going to go? First off, which ring is going to be preferred? This ring has a group 1, that has a group 2. Both rings have a phenyl. I mean, if you look at that, it has a methyl and a phenyl. This one has a methoxy and a phenyl. So the phenyl is pretty much a 1. Which ring is more activated towards EAS? This ring. Okay, now, is it going to go ortho to the methoxy or meta? Ortho. If you nitrate this, you get, I'll just draw it right there. You get a nitro right there. Let's take a quick look at chlorine. I don't think this is written anywhere. When you nitrate this, what do you get? So it goes here, so it goes there. What's directing there? These are your 2 substituents on this ring. What is this substituent? That's an sp3 carbon. What type of donator is it? Induction, but director, it's a ortho-para. Did the nitro go ortho-para to the sp3 carbon? No, it did not. What is this director? It's drawn kind of funny. I mean, if we draw it just straight up, it's a benzene ring bonded here. So it's a pi bond. What type of director is a pi bond? Group 2, ortho-para. Okay? Did the nitro go ortho-para to this group? Yeah, with para. So both of these are group 2. But apparently this ring is a greater director than the methyl. That's because it's not only just one alkene, it's multiple alkenes in the form of an aromatic. There's lots of cations that you could get, and you can put the cation over here into this ring by resonance. Now, ortho would be here. Now, who's to say you don't get other products? The yield on the nitro is, anybody calculated the yield yet? You know, if you get 50–60% yield, well, what was the other 30 or 40%? It could have, you could have just lost some of this, or it could have been another isomer. Not sure unless you isolate and analyze all stuff and don't throw out any filtrates. Okay.
Hey, Dr. Steve.
Hey.
Since H2SO4, when it's used to like extract a beta hydrogen, it reforms sulfuric acid. Is that something like you don't need a lot of it to like do like a repeated nitration?
Catalyst, you need 1 molecule. So next time, just weigh out 1 molecule. Right? Direct, all you need is 1 molecule of catalyst. It does it, it's reformed, you do it again. Typically, hard to weigh out just 1 molecule there. Okay, let's move to Friedel-Crafts. In terms of EAS, we halogenated, we nitrated, we sulfonated. I think that was it. Nitro we can reduce to the amino. Friedel-Crafts is when you put carbons on the ring. There'll be two types of Friedel-Crafts. Alkylation, which we put a alkyl on the ring. We'll also do acylation, where we put an acyl group. An acyl group, if you may not know yet, is basically a ketone type group, carbonyl. You may remember the acylium ion from mass spec. Here, the E plus is going to be a carbocation. Our good old friend, the carbocation. Do you know how to make carbocations?
Yeah.
Tell me a way to make a carbocation.
Attacking H.
What attacks the H? A pi bond, you can protonate it and get a carbocation. Yeah, what's another way? Can you make a carbocation from alcohol? Protonate the OH, ionize. It's best if the original alcohol was what type? Tertiary, not primary. Okay. Any of the ways you've ever made carbocation, you're on your way to just doing some benzene chemistry. If you've got a benzene ring and a carbocation, they're going to react by an EAS mechanism. Okay. Friedel-Crafts first described in 1877. It allows for carbon-carbon bond formation. And historically, anytime you make carbon-carbon bonds, it's always been very significant. It really advanced the organic chemistry along the way. Like Grignard. Grignard reaction is making carbon-carbon bonds. Friedel-Crafts. Later on, we'll see the Wittig reaction. Carbon-carbon bond. Okay, here's a reaction. You take benzene, isopropyl chloride, or you could call it 2-chloropropane. Throw in a Lewis acid, aluminum trichloride, you can get isopropyl benzene plus HCl. Okay, so we make this carbon-carbon bond. First step of the mechanism is a lot like if this was Cl2. If this was chlorine, what would you do first? We do what? We complex with the aluminum to make the chlorine positive, and then we would attack this chlorine, kick off that chlorine. Well, the same thing happens here. These electrons coordinate with the aluminum, and we get this complex formed with the Lewis acid. How do you make OH a better leaving group? Protonated, usually with proton, acid, and proton. You can also make halogen a better leaving group, but not by protonating it, but by complexing it with the Lewis acid. Typically you don't protonate halogens, but you can get them to become positive by complexing them with Lewis acid. At this point, we're actually going to ionize this off, and what does this give? Carbocation plus AlCl. I'm going to keep one chlorine drawn out. We can get carbocation formation. And now we just attack this just like we attack any E plus. Electrons here. And so I did something like this. I'm basically illustrating the pi bond is moving up to attack the carbocation, leaving the bottom carbon plus. There's an H up there. Resonance structures you can do. I'm not going to show resonance structures. What's next? Something takes the H, restore the aromaticity. The aluminum can say, hey, chlorine, take a hike. Chlorine's like, okay, I'm out of here. I'm taking my electrons with me. I'll go bond to this H, and these electrons move in here. What do we produce? That, and we reform what? Lewis acid reformed. So that's a good old Friedel-Crafts alkylation. We put an alkyl group on the benzene ring. The electrophile was in carbocation. What type of carbocation here? Primary, secondary, tertiary? Secondary. What types are best? Tertiary. Secondary and tertiary best. I would never show a primary carbocation. Sometimes a textbook will show it. For us, I've always said, do not show a primary carbocation. Secondary is okay. What are carbocations prone to do? Rearrange. Rearrange. Will this one tend to want to rearrange?
No.
No, there's no need for that one to. Anytime you do carbocation chemistry, you got to watch out for rearrangements.
So if the chlorine was on the end, would it rearranged and then we needed some time?
If the chlorine was on the end, you'd have to first form a primary cation. Right? That's why I don't even want to answer that question. Some books will show it. You can actually get a product from a primary. Because what works here? Yes, a primary halide does work. So you have to say, well, is it making a primary carbocation? I don't want to go there. It might, or it may be more like an SN2 type, where the ring attacks and kicks off the chlorine at the same time. Some books will show primary. I just don't want to do that. Chlorine is most common just because chlorine is the most common halogen. Now it does not work, the chlorine, the halogen cannot be on an sp2 carbon. So it does not work with these. But I'm talking about the electrophilic portion. Other routes to carbocations, what we just mentioned. You can make a carbocation from alcohol. Here's what we're familiar with. Take an alcohol, H+. We can protonate, we can ionize, make carbocation plus water, right? It's good old carbocation. That's best with tertiary alcohols, although it does work with secondary as well. Sometimes you can also use a Lewis acid with an alcohol. And a common Lewis acid with alcohols is BF3. Boron is above aluminum in the periodic table. And the same thing, these electrons coordinate with the boron MTP orbital. And you get something like this. And then the oxygen can ionize off, giving you your carbocation. So that's an example of using a Lewis acid for an alcohol. BF3 is commonly used. As somebody mentioned before, we've also seen making carbocations from alkenes. You take an alkene, react it with H+. What is this going to give?
Secondary carbocation.
Are you going to make cation on the left or right? Left. On the left, okay? That's good old alkene chemistry. That's like the first reaction we ever saw in Organic 1, right? Protonation of an alkene. What acid would you use here? Would you want to use HBr here?
No.
No, because if you use halide, halide would attack here. You want to use something where the conjugate base will not attack. You want your ring to attack the carbocation. So typically you use sulfuric, phosphoric, HF, etc. Typically you don't use a HX. We'll look at some examples in the, sort of the miscellaneous pages. But let's look at your Friedel-Crafts alkylation is not a super great reaction. The acylation, which we'll look at later, is better. Why is alkylation not such a great reaction? Here's some reasons why. The first is, it fails when you have strongly deactivating substituents. Of the 4 groups, which ones are strongly deactivating? 4. That's group 4. Now your strongly deactivating substituents are sometimes also called metadirectors. Why? Because they are. Group 4 is also metadirectors. So another way to say this is, it fails with metadirectors. For example, you take nitrobenzene and try to do the reaction we just showed on the previous page, you won't get any product. Because a nitro is a strongly deactivating metadirector. Now you can do all the other reactions with nitrobenzene. You can chlorinate, you can sulfonate, you can actually nitrate it again. But for some reason, the Friedel-Crafts doesn't work with metadirectors. Kind of odd that it does. Nitrobenzene is actually a common solvent for Friedel-Crafts reactions because it's inert. It doesn't react. Number 2, Friedel-Crafts alkylation. Actually, these first 2 are going to fail when we get over to acylation as well. Friedel-Crafts also fails with anilines. Why? I'll refer you to number 1. Because it always fails with deactivating substituent. Is an amine a deactivating substituent? Now it is. The amine will complex with your Lewis acid. Of course, why not? Why would you expect these lone pairs to complex, but that lone pair not to? The amine complexes with the Lewis acid, turns it into a deactivator. This is what we showed at the very beginning on that table, where I had the arrow going down to the bottom, right here. And at this point, I would refer you to number 1. Because now it's a strongly deactivating substituent. You can also argue that it just ruins your Lewis acid. Now here's the thing. A phenol or a methoxy, those will do Friedel-Crafts. Apparently they don't complex enough to cause it to not work. Okay? So phenols, etc. do work. Also over here, this guy would work. Because this lone pair is not that basic, right? I was in a pure. So this, you can do Friedel-Crafts of this, just not of your free anilines. Please look ahead, guys. There's other problems with Friedel-Crafts. We'll move on to acylation. I meant to pass something out. You can get it today if you want. If not, you can get it on Wednesday. I'll put 2 stacks here.